We've previously talked about Boyle's law, and Boyle's law was really comparing pressure and volume. And Boyle told us that pressure is inversely related to volume. So if you increase pressure, you decrease volume, granted that you kept temperature and the number of particles the same, or the amount of substance the same. Okay, now another guy named Charles, who was a French mathematician and a physicist, came along and he noticed a relationship between volume and temperature. He noticed that volume is directly proportional to temperature, and the temperature specifically has to be in degrees Kelvin. And so this is a rough plot. He noticed a linear plot of volume versus temperature. Okay, and so when they did this in degrees Celsius, they were able to extrapolate a point where the volume would reach 0. It would be approximately at negative 273 degrees Celsius. And so we called that point 0 Kelvin, or absolute 0. And that's what that exactly means, because at absolute 0, molecular motion virtually stops. If we get any colder than that, then if you notice, if we go any further, we'll get a negative volume. Is this physically possible? Absolutely not. You can never have negative volume. You can never have negative mass. So at negative 273 degrees Celsius, or 0 Kelvin, absolute 0, molecular motion virtually stops, and basically we can't get any colder than that. So remember, the degrees Celsius and the degree Fahrenheit scales are relative scales. Because we have plenty of water on Earth, we decided to conveniently call water freezing 0 degrees Celsius and water boiling 100 degrees Celsius. So we made those scales up, whereas the temperature scale is actually telling us about molecular motion. Okay, so that's very important that the temperature has to be in Kelvin. Anyhow, so we found that, again, if you take a balloon, you've seen in your slides, if you take a balloon and you put it in ice water, then you switch it over to boiling water, you'll see that the gas expands, because as you increase the temperature, you increase the volume, because remember, as you increase the temperature, molecular motion increases as well. And this is very similar to your car. When it gets cold outside, you notice that your tire pressure deflates. So you get flatter tire, right? That's because as it gets cold, the volume contracts, right? The volume gets smaller. But if it gets hot, you don't want to have tires that are inflated too much, because if it gets hot, then your tire will expand too much. So that you want to find that perfect balance. Okay? So based on this idea, we know that we can come up with Charles's law. And Charles's law is V1 over T1 is equal to V2 over T2. Okay? So let us do an example in which we use Charles's law. Okay? A sample of gas has a volume of 2.8. Okay, so we have a sample of a gas that has a volume of 2.8 liters. So volume 1 is 2.8 liters, and an unknown temperature 1. Then we know when the sample is submerged in ice water at 0 degrees Celsius, the volume decreases to 2.57 liters, okay? What is the initial temperature in kelvins and in degrees Celsius, all right? So let's see. Since here we notice that going from volume 2 to volume 1, there's an increase in volume from here to here, then there should also be an increase in temperature. So we know that we should get a T of something greater than 0 degrees Celsius. But let us use Charles's law to know exactly how to solve this. V1 over T1 is equal to V2 over T2. We are trying to solve for T1 over here. So you can either plug in the numbers first and then solve for T1, or you can rearrange the equation. The way that I like to do this is that I like to plug in my numbers first. So I have 2.80 liters over T1. And then V2 is 2.57 liters over my T2. But what's the problem with T2 here? It's in degrees Celsius. You don't want to do that. Remember that? You want to convert all your numbers to Kelvin. So this is 273.15 Kelvin. All right? 273.15 Kelvin. All right. And then you algebraically solve for this by bringing your T1 over here and then multiplying by the reciprocal of this number. Okay, so the reciprocal of that number is 273.15 Kelvin over 2.57 liters. And then don't forget though that this number is here on the top, so this is times 2.80 liters. Okay, and this is your T1. Okay, you see how your liters cancel out and you're left with Kelvin? Let's plug that in to see what our T1 is in Kelvin. 273.15 times 2.8 divided by 2.57. So it should be 297.59 Kelvin. So we'll call that 298 Kelvin. Okay, so we've solved that in terms of Kelvin, but let us see how much is it in degrees Celsius. So remember, Kelvin is degrees Celsius plus 273.15. Okay, so degrees Celsius then should be Kelvin minus 273.15. So whatever Kelvin you had here, 298 minus 273.15. Let us do 298 minus 273. And if you just want to use 273, that's fine. Your book uses that. So in degrees Celsius, it'll be 24.85 degrees Celsius or 25 degrees Celsius. Okay? So now we've solved the problem. Okay, now I want you to give this a try, and I want you to take this example. A gas in a cylinder with a movable piston has an initial volume. Initial volume is 88.2 milliliters, and is heated from 35. So because it says from, that's T1, 35 degrees Celsius to 155 degrees Celsius. What is the final volume of the gas in milliliters? Okay, so remember our law is V1 over T1 is equal to V2 over T2. And this time we're trying to solve for V2. Okay, so let's plug in V1, which is 88.2 mils. And because we want the second volume in mils, we can just leave it that way. We don't have to do conversions, all right? T1 is 35 degrees Celsius, but we should add 273 to that, okay? So we will just add 273. And so that will give us 308 Kelvin. And this is 155 plus 273 gives us 4 plus 273. This gives us 428 Kelvin. So T1 again is 308 Kelvin here. And V2 is unknown. And we have T2 at 428 Kelvin. So this is a simple algebraic problem. We will just multiply both sides by 428 Kelvin. And you see the kelvins cancel and we're left with milliliters, which is exactly right because milliliters is a unit of volume. Okay, so 428 times 88.2 divided by 308. This gives us a volume 2 of 123 milliliters. Okay, and were we expecting this? Most definitely, because look, from T1 to T2, we're increasing the temperature. So we should be increasing the volume of that. Now let's think about another idea in terms of conceptually speaking. A volume of a gas is confined to a cylinder with freely movable piston at the end. If you apply enough heat to double the Kelvin temperature of the gas, what happens? And we want to assume constant pressure. Remember that temperature and volume are directly proportional and they're linearly proportional, which means that if we double the temperature, again in Kelvin, we should double the volume. Is that right? Now, I stress this. Notice it says if you take the temperature and you double it, but it must be Kelvin temperature, then you double the volume, okay? If you have the temperature in Kelvin, you have the volume. It's directly proportional relationship. But if I had said you double the temperature from, let's say, 25 degrees Celsius to 50 degrees Celsius, are you going to double the volume? Absolutely not, because you have to convert this into Kelvin first, and then you can only base this on Kelvin relation. So then you'd have to convert this to Kelvin and convert this to Kelvin and then see the relationship between the two. You cannot say that volume doubles if the temperature doubles in degrees Celsius.